Hello everyone, this is Mehru, and today I'm going to present our work on robust path planning and control for polygonal environments via linear programming. The problem of path planning is finding a path from an initial state toward a goal state while considering collision avoidance given the map of the environment. However, the biological system can navigate robustly towards a desired door without precise blueprint of the floor and without its precise location. The performance of the biological system is the result of a complex and not fully understood mechanism. In this work, we aim to narrow the gap between the path planning algorithms and the biological systems by synthesizing the output feedback controller that are robust to imprecise map knowledge. In this paper, we integrate the high-level path planning and the low-level regulation tasks such that the controller can navigate by directly using measurements instead of assuming full state knowledge, and the controller is robust to the significant changes in the map. Existing works on path planning can be classified into categories: combinatorial path planning and sample-based path planning. One of the well-known combinatorial path planning algorithm is cell decomposition method, where the complex environment is decomposed to a set of cells and avoids obstacles by planning a straight path in individual cells. Sample-based algorithms are popular due to their good practical performance and their probabilistic completeness. Extensions of RRT algorithms like closed-loop RRT and safe RRT algorithms can expand a tree from initial state towards a goal state by sampling control inputs. The common trait among all these works is the use of a full state feedback, but in this work, we design an output feedback controller by directly using measurements available to the agent. In this work, we synthesize a set of output feedback controllers on a convex cell decomposition of any generic convex polytope. We consider output feedback based on any affine function of the states, and we design a controller over entire convex region rather than single points. Then we design constraints in terms of a control Lyapunov functions to ensure stability and control barrier functions to ensure safety through all the states in the cells, while automatically balancing the two aspects to maximize robustness. Then we solve the min-max optimization problem by linear programming to find the controller. Assume we have a polygonal corridor. We can decompose this polygonal environment to a set of convex cells as xi, and we can define each cell by a set of linear inequalities, such that the union of all cells is equal to the original polygon. For every cell, we assume we have a linear dynamics defined by matrix A and matrix B, and the states belong to a convex sets, and the actuators are bounded. Assume we have a convex cell I with an exit face which we want to pass through. We define h of x as a barrier function, which AH and BH are defined by the boundaries of the cell. Vector z is the normal of the exit face, and xe is a point in the exit face. We define v of x as the Lyapunov function in terms of z and xe, which represents, up to a constant, the distance between the current system positions and the exit face. If we have the differentiable function h of x, we can define the safety set C such that h of x is greater than 0 in the set and equal to 0 on the boundaries of the set. Set C is called forward invariant if we start from a point in the set, we remain in the set for all t. The relative degree is defined as the number of times we need to take the time derivative of the output to see the input. In this example, we have x.1 equal to x2, x2 dot equal to minus x1 plus u, and the output is equal to x1. If we take the first derivative of the output, it would be x2, and the second derivative of the output is in terms of the controller. So the relative degree of this example is equal to 2. Barrier function h is exponential control barrier function if there exists a constant ch and controller u that satisfies the control barrier function constraints to guarantee the safety. On the other hand, we assume we have a differentiable Lyapunov function v of x If there exists constant CB and controller U that meets control Lyapunov function constraints, then V of x is the exponential control Lyapunov function and guarantees the stability. We defined a barrier function for a cell with a control system of x dot equal to ax plus bu. For simplicity, we assume the relative degree of h of x is equal to 1. To write the safety constraint by the control barrier function for a cell, we substitute the h dot and h in the CBF constraints that result in a linear constraint in terms of x. We want to find a controller U such that the CBF constraint is met for all points in the cell. Similar to the CBF constraints, substituting Lyapunov function v of x in the CLF constraints result in a linear constraint in terms of x. We want to meet the CLF constraints for all points in the cell. To design a controller, we define a landmark as a point in the environment that its position is known. We divided the state of the agent in two parts. X pose, which shows the positions of the agent, and we don't have access to that, but the agent can measure the relative displacement between the robot's positions and the landmarks. And X of dynamics, which shows the rest of the states, and we assume we have a direct access to that. We assume the agent can only measure the relative displacements between the robot's positions, which is X pose, and the landmarks in the environment that corresponds to the output function Y. L is a matrix of landmarks locations, and V represents the vectorized version of a matrix. The landmarks are not necessarily belongs to a cell. Our goal is to find a feedback controller that, given Y provides an input U, drives the system towards an exit phase while avoiding obstacles. We propose a controller as a function of the output where K1 and K2 are the feedback gains that needs to be designed. The controller feeds back the linear combinations of displacement measurements. Our goal is to find control gains that maximize the motion of the robot towards the exit phase while avoiding the boundary of the environment by satisfying the CLF and CBF constraints respectively. In practice, we aim to find a controller that satisfies the constraints with some margin. We use SP margin to achieve minimum distance from the obstacles and SL margin to achieve the finite time convergence. The control gains should satisfy the CLF constraints and CBF constraints at every point in the cell. We handle this type of constraints by rewriting the problem using a min-max formulation. WB and WL are the user-defined constraints defining the trade-off between the barrier functions and Lyapunov function constraints. Larger WB implies solutions moving away from the walls, while larger WL implies solution moving faster toward the exit phase. In this optimization problem, all constraints and objective function are linear, and X belongs to a convex set. An inner maximization problem are linear programming. So we replace the inner maximization problems with their dual forms and change the min-max problem to a min-min problem. Now the min-max optimization problem converts to a min-min optimization, and it's equivalent to the minimization problem over the dual variables and decision variables. By solving the minimization problem, we can find control gains that satisfies the CLF and CBF constraints for every point in the cell. To validate our proposed approach, we implement our method to two non-simply connected environments to find the output feedback controller. Then, we deform the environment and implement the same controller to represent the robustness of the controller. Here we have two examples. The objective of the first example is to converge to the stabilization point, and the objective of the second example is to patrol the environment by converging to a path and then traversing the same path. Note that the choice of the first and second integrator system is independent of the planning objective and complexity of the environment. In our first example, we have the polygonal environment with first-order systems. We then decompose the environment into a number of convex cells, and then starting from three different start points, we drive the agent toward the goal point while satisfying the safety and stability constraints. Then we deform the environment significantly and drive the agent toward the goal with the same controller without replanning. In this example, we want to find a controller for the second-order system to traverse through the environment while satisfying the stability and safety constraints. Then we enlarge the obstacles and use the same controller. The agent moves through the environment without violating safety and stability constraints. And when the obstacles rotate 45 degrees, the agent moves through the feasible path to cover all the environments with similar control gain. To conclude, we propose a novel approach to design an output feedback controller with cell decompositions through the linear programming. We define a controller such that it depends on the relative displacement measurements with respect to set of landmarks. We transform the min-max optimization problem to the minimization problem and define a controller which is robust to the significant changes of the environment. At the end, we validate our approach on the first and second order control systems. For the future, we plan to add smoothness constraints for passing through the cells. We will study the sampling-based algorithms to remove the polygonal environment constraints and cell decomposition assumptions, and we will provide theoretical proof for the robustness of the controllers that we empirically demonstrate. Thanks for listening to my presentation.